Good morning, students. Here is a question that I found students struggled on. This is a question that deals with a car taking a curved road that is actually banked. But the banking is not enough, and we need to consider friction also. And we got to find the minimum coefficient of friction required to keep the car on the road. So here is the question. A banked circular highway curve is designed for traffic moving at 61 km per hour. So it's banked for that speed. The radius of the curve is 211 meter. Traffic is moving along the highway at 43 km per hour on a rainy day. That means on a rainy day, you see friction is less. And what is the minimum coefficient of friction between the tires and the road that will allow cars to take the turn without sliding off the road? Assume that the cars do not have negative lift. So that means the normal force is just enough. And so the car is not pressing down on the road. So first of all, we need to find the angle of banking. So here is the free body diagram. The vertical arrow shows the weight of the car, mg, and the arrow that's perpendicular to the road is, of course, the normal reaction. And the normal reaction is broken up into its components or resolved into its components because we got to get the x and the y components, right? So that's why the weight is mg, and this well, that's not Fn, that is, Fn is the bold arrow. And I'm trying to show the axis there, the x and the y axis is as usual. This is not to be confused with an object moving on a ramp where we usually take the x-axis to be along the ramp. This is not like that. So we go back to the original where x is horizontal and y is vertical. That's why this is the normal reaction. And the vertical component is Fn cosine theta, because that becomes the adjacent side. And the other one, which is the horizontal, is Fn sine theta. So we can see that Fn sine theta actually provides the centripetal force because it's towards the center of the circle. Okay, so let me speed this up a little bit. Fn sine theta provides the centripetal force, which is, as we know, mass times velocity squared by radius. So we get that. And Fn cosine theta balances the weight. So Fn cosine theta is equal to mg. So once we get that, we divide the first equation by the second one. The Fn's will cancel out and we will have tan theta. The masses will cancel out and we will have tan theta is v squared by rg. So that's what we get. Tan theta is v squared by rg. And from which we can substitute the values of the velocity and the radius. But the velocity is given in as kilometer per hour. So you got to change that into meter per second. This is the quickest way. Multiply by 5, divide by 18, and you get it as 17 meter per second. So plug in that value, and the radius is 211 meters. So once you plug in that, times 9.8, and find tan theta, then take the inverse of that, we will be able to find theta as 7.9 degrees. So that is the angle of banking. That's how this road has been built. So now we go to the second part. In the second part, the cars are moving along at 43 km per hour. So let's change that into meter per second first before we do anything else. And by the same process, we get 12 meter per second. And then here is the thing. We try to find the acceleration. We know that the centripetal acceleration is v squared by rg. It's v squared by r. Centripetal acceleration again is v squared by r. So I put a prime and v prime because that's the new speed there. And this diagram is very important because the centripetal acceleration is towards the center of the circle, and that means it's horizontal along the x-axis, and we have to break it up into the parallel component, means parallel to the road, and perpendicular to the road. So we'll call them the A parallel and A sub perpendicular. So the A parallel, from the geometry of this diagram, you can see that that is theta, and therefore this is going to be cosine. So that's A prime cosine theta, and the other one is A prime sine theta. So now that we have got this, now let's look at the weight. See, the weight mg, has also got to be resolved into parallel and perpendicular components. You know that the weight always acts vertically down, and we're going to break it up along Fn. We get mg cosine theta. In fact, that's along Fn but opposite to it, so we get mg cosine theta. And the other one is mg sine theta, which is along the road. Okay, so once we have resolved that, we can use those two components to move on and to find that mg sine theta is acting down the road, while friction, static friction in this case, is acting opposite. So static friction is trying to keep the car on the road. Therefore, the net force is mg sine theta minus Fs. And I have shown a friction here. You can see that friction is opposite to mg sine theta. So that's why the net force is mg sine theta minus Fs. And by Newton's second law, the net force is equal to mass times acceleration. And then when you look at the perpendicular component, you have Fn and you have mg cosine theta opposite to it. So it's the net is Fn minus mg cosine theta. That is equal to m times A perpendicular by Newton's second law. So since we don't have space here, we'll go on to the other one, and we get, I'm writing the same things, actually copying from the other side. So these are the equations that we had from the previous page. And then we will substitute the values of A parallel and A perpendicular. In fact, before that, we can make Fs the subject here. Fs is mg sine theta minus ma parallel. And from here, Fn can be made the subject. Now, why are we doing that? Because we are asked to find the value of the coefficient of friction. And what is the coefficient of friction? It is the ratio of the static friction to the normal reaction, isn't it? So once you take that ratio, you divide the terms, the equations, one by the other, and we have this setup. That's simple algebra from there. And then all we have to do is substitute the values of mass, g, theta, and A parallel and A perpendicular, all that. I have not done those. When you substitute all those values, you will get the minimum coefficient of friction as 0.069. And that's how we do this problem. Thank you.